So let's start with the easiest type of problem to solve, and this is a Ka problem. So with a Ka problem, typically what we're given is an acid, maybe its conjugate base, and we're asked to find the concentration of H plus or the concentration of any of the reactants or products. Maybe we're asked to find Ka. The point is we have a weak acid dissociation and we're looking at something about its equilibrium. So in this problem, we have phosphoric acid, H3PO4, doing a single deprotonation to give us H plus and H2PO4 minus. And we are told starting concentrations are 1 molar for the H3PO4 and 1 molar for the NaH2PO4. And Ka is 0.0007244. Now, a few things to comment about this. Students typically make a mistake here and they see the sodium and say, well, the sodium should be on the left. Everything goes on the left. This is a reversible reaction. Things can be both products and reactants, and they're going to react. This Na here is a spectator ion. We can't buy H2PO4 minus 1 off a shelf. There always has to be a counter ion in it. So if you go back to your solubility rules, anything that's a column 1 metal is going to be soluble in water. So typically when we see something like sodium or lithium or rubidium or potassium, something out front we know that's going to do nothing with the water and it's just there to deliver the anion. So if you're given this compound, something with a column 1 metal or something that's soluble in water but it looks like your counter ion, that's what this is. This is referring to the concentration of the H2PO4. Now, in this problem, we're going to solve for the concentration of H+, but the approach is the same for every single equilibrium problem. There's 3 things you need to solve this expression. First of all, we know at equilibrium KQ equals Q. So we know that Ka, the number here, has to equal our functions of concentration. So that's 1, KQ equals Q. The second is that we need our expression for Q. And our expression for Q here is the concentration of H2PO4 minus 1 times the concentration of H plus all over the concentration of H3PO4. So second, we need our expression for Q. Now these numbers here represent the equilibrium concentrations. The third and final thing we will need for every single equilibrium problem we solve is an ICEE table. So our ICEE table we've got H3PO4, H plus, and H2PO4 minus 1. Now, the ICEE table is how we're going to connect concentrations to this K equilibrium constant and how we're going to connect it to Q. So, once you've got these 3 components, start populating with what you know. We know the initial concentration. So for any Ka problem, we're going to assume we don't have any H plus in solution, that everything is going to come from our weak acid. Given a starting concentration of 1 molar for the H3PO4 and 1 molar for the H2PO4. The changes here, if you go back to previous videos, minus X, X, and X. So at equilibrium, it's 1 minus X, X, and 1 plus X. We are not given the equilibrium concentrations, but we are asked to find them. So this square here is ultimately where we're trying to get to, the numerical row. So, since we know Ka, and we don't know how far the reaction went, we're going to use this row and substitute in our expression for Q. So we're going to get that the concentration of H plus is X, concentration of H2PO4 is 1 plus X, and the concentration of H3O4 is 1 minus X. I would advocate you solving this symbolically before you try to start putting in numbers, particularly with Ka. Now this is a nice value of Ka because it's a fairly big number. But when you start dealing with things like 10 to the minus 6, 10 to the minus 5, this can become kind of a daunting thing to carry around in your calculations. So hopefully you can see it up here. I'm going to rearrange. Get Ka 1 minus X, X plus X squared, distributing the X, multiplying the 1 minus X over to Ka. I'm going to get X squared equals, X squared plus, trying to do this in my head, Ka plus 1 X minus Ka times 1 equals 0. So go back through, see if you can rearrange the algebra to get this solution. But what we'll get is a quadratic equation. X squared plus Ka plus 1X minus Ka times 1 equals 0. It is a quadratic equation. You should know the quadratic equation from algebra when you took it. When we work it out, we're going to end up with 2 roots. Now, how do you know which root is the correct root? Well, we've got our n values down here. Now, this is kind of an easy problem, particularly these Ka problems, because, well, concentration of H plus has to be positive, and typically with these quadratics we end up with a positive and negative root. So we know the extent of reaction can't be negative because that would tell us the concentration of H plus is positive. If I do work it out, I get that X equals 0.714. This is the only positive root. So that tells me then my extent of reaction was 0.0714. Now let's say I want to calculate the concentration of H3PO4. Well, I just have 1 minus that number. So I get roughly 0.993. If I want to know the concentration of H2PO4, I would add that number, so I'd have 1.01. And I would have the ICE table completely filled in. Now, what are the other flavors of this type of problem? What if I asked you what Ka was? I'd have to give you the equilibrium concentrations. I would fill in this row, take the values I got in this row, plug in my expression for Q, and figure out what Ka is numerically. But this is how you basically approach any type of Ka problem. Go through, get your 3 expressions. KQ equals Q, Q equals your functions from your function of concentration from your reaction, and fill in your ICEE table.